Welcome to page 3 of the notes. Here's a Laplace transform of some basic functions. So we can actually just refer to this whenever we have a Laplace transformation of this form. So like the Laplace transformation of 1 is just 1 over s. That was our first example. Our third example, the Laplace of, a variable to the n power will always be n factorial over s to the n plus 1, whatever n may be, whatever power that may be. Now, if I have a Laplace transformation with e to some alpha t, then that's always going to be 1 over s minus the alpha, whatever that constant is in the exponent with the t. Sorry, coefficient. And so here you have sine and cosine. So whatever that k is, whatever that coefficient with t is, it's going to be k over s squared plus k squared. Or if we have cosine, it's going to be s over s squared plus k squared. All right? And then we have the hyperbolic sine and hyperbolic cosine, where it's very similar to our normal sine, except for it's, instead of plus, it's minus. And the same thing with our hyperbolic cosine. All right, so one thing is that the Laplace is a linear transform. That means I kind of can distribute my Laplace to every term in my function. So here I have two terms, alpha f of t plus beta g of t, where the alpha and the beta are coefficients. So I can pull those outside of my function, and I can just take the Laplace of the actual function. So because those are, constant coefficients, I can pull those out, and so I can just do the Laplace transform of f of t and the Laplace transform of g of t, and that's what I'm going to do. So like here, look at example 5. I want to do a Laplace transform of 2t minus 1 to the third power. First thing that I want to do is I want to go ahead and do, well, what is 2t minus 1 to the third power? And here I can write the polynomial form of this, and so I'm just going to go ahead and multiply 2t minus 1 times 2t minus 1 times 2t minus 1. I'm going to take 2t minus 1 to the third power. When I do that, I get 8t to the third power minus 12t squared plus 6t minus 1. All right, and now I can treat this like it's with the linear part, and I'm going to just pull the 8 out and just do the Laplace transform of t cubed. I'm going to pull the negative 12 out and do the Laplace transform of t squared. Pull the 6 out, do the Laplace transform of t, and I pull that negative out and have negative 1 Laplace transform of just 1. All right. Now, the Laplace transform of t cubed, well, my n is 3, so I'm going to have n factorial, so 3 factorial over s to the 3 plus 1, or s to the 4th. And so I have 8 times 3 factorial over s to the 4th. Minus 12, again, t squared, so 2 factorial over s cubed, plus 6, and then I just have t, so that's just 1 over s squared. And then minus 1, and that's just 1, so we know that's 1 over s. And so 3 factorial, if you have trouble remembering what factorial is, it's just when you multiply all numbers before 3 by each other. So 3 factorial is just 3 times 2 times 1. So 3 times 2 is 6. 6 times 1 is just 1. So that's 6. So I have 8 times 6, which gives me 48. S over 4. 2 factorial is just 2 times 1. So 12 times 2 is 24. So minus 24x cubed. I have 1 over s squared, 6 times 1, 6, and then just minus 1 over s. And I'm finished. All right, so all I wanted to do was write the polynomial form of 2t minus 1 cubed, and then I can just use all of my basic functions to find the Laplace. I don't have to do the integral with e to negative st, which it will save me some time. All right, example 6, I'm going to find the Laplace transformation of cosine of 5t plus sine of 2t. So again, I have two terms, so I'm going to put the Laplace to both terms. So the Laplace of cosine 5t plus the Laplace of sine of 2t. So for cosine, the k value is 5, and if I go up to here, and I know that it's s over s squared plus k squared, so it's going to be s over s squared plus 5 squared, which is 25. K is 2, so for sine it's k, so 2 over s squared plus 2 squared. 2 over s squared plus 4, and I'm finished. I don't have to combine these, I'm finished. And so there I've transformed this function into a new function. Alright, now the next thing we're talking about is exponential order. A function is set f is said to be of exponential order if there exists constants c where m is greater than 0 and t is greater than 0, such that the absolute value of f of t is less than or equal to m times e to the ct for all t greater than the kappa t, which means that the graph of f on the interval from t to infinity does not grow faster than exponential m e to the ct, where m is basically the coefficient of whatever function that we're dealing with, and c is the part with the actual exponent, or the part that is, inside of our function. And then t is basically where our interval is going to start. So here we have t, all right? It's said to be of exponential order because the exponential function m times e to the ct grows faster than just t, all right? And here you can see that if we were to label the m, it's just 1t to the, and that's it. You don't need no power there, so it's just e to the t is what we're going to compare it to. So e to the negative t is what we're going to compare this to, and when we compare the two, we see that our exponential, once again, is going to grow faster than e to the negative t. So now here we are comparing 2 cosine t times 2e to the t. M is 2 in this case because we're multiplying the function by 2. So here we would multiply e to the t by 2. And of course, 2e to the t is going to go faster than 2 cosine t. Now the reason why we need exponential order is because we're not going to be able to use e to negative st as our kernel for our Laplace transform if, our function is said not to be in exponential order. So that's the key here. I'm not going to give you any that you're going to have to solve if it's not of exponential order, because you're not going to be able to do it. Not with the methods that not with the method that I've shown. All right. Now the last thing is for a piecewise continuous function from 0 to infinity, and of exponential order. So if it's of exponential order, and we're going from 0 to infinity, that is continuous, then our Laplace of f of t exists when our s is greater than our c. So f is a piecewise continuous function. Our function has to be continuous from 0 to infinity, and if any interval there are at most finite numbers of points at f has removable step discontinuities. And so we're just going to be able to take the Laplace transform of piecewise defined functions, but we're going to have to break up the 0 to infinity part, and I will show you that in the next page.